enjoying some good wines, and they don't want to hear about storage. So should we wait 1 more minute before people finish a glass of wine? Yeah, I think so.
Storage is so exciting. Why don't you bring your wine in here?
No, I just moved some few months ago. I was working a lot on DPDK, and now I need petabytes of data for medical imaging. So yes, networking and storage are pretty close, I think. So do we still have some people which are going to join? Okay, let's wait for the last people to sit down, and then we'll make the introductions. Okay, so the next talk will be about storage and DPDK. I think that's a story that started some few years ago with the SPDK. And as you know, IOs can be many things in a CPU. It can be packets, or it can be a block for storage. So let's see what it will be. So we have Fiona and Darek. Thank you.
Darek's going to start.
Yep. I know it's Friday, 4 p.m., and we already start to think about the weekend, but please stay with me for this presentation and hopefully the next one as well. Right. Hi, I'm Darek. This is Fiona, and we would like to tell you how DPDK is used in some of the most performing storage stacks. So we'll shed some light onto unusual DPDK use cases. Right. First, we'll tell you what SPDK is. It stands for Storage Performance Development Kit, a project that was initially called DPDK for Storage, so we already get the idea. And we'll tell you how it integrates DPDK in a bunch of different areas. So we've got Cryptodev, CompressDev, memory management, PCI access, and vhost. Right, SPDK. Just like DPDK polls PCI NICs, SPDK polls PCI and NVMe SSD drives. So the same Userspace poll mode techniques that apply to DPDK apply to SPDK as well. So SPDK, rather than reinvent the wheel, it uses DPDK as a dependency. So in SPDK repository, there is a DPDK Git submodule, and it usually points to the latest, most recent DPDK release. It's very frequently updated. Most information about SPDK can be found on our website, SPDK.io. SPDK has a community that's completely separate from DPDK, right? So first and foremost, SPDK is a project on GitHub. It's also a project on GitHub where we do our patch submissions and reviews. And then we've got a couple of different communication channels. We've got a mailing list. We used to have IRC, now we have Slack. We have Trello for public backlog. And we do weekly community calls. And also bi-weekly GitHub issue review meetings, or bug scrubs, as I like to call them. So let's take a look inside SPDK. This black line in the middle, slightly to the right, separates SPDK codebase between the actual SPDK code and DPDK code. And I think it's placed fairly accurately in terms of the ratio between the two. So about 1/4 of what SPDK does is actually handled by DPDK. And I'm not saying that SPDK is a few times bigger than DPDK. It's just that SPDK uses only a few selected libraries from DPDK. So starting from the bottom, we've got memory management, PCI access, which practically make RTE-EAL. Then we've got compression, so CompressDev, encryption, Cryptodev, and RTE vhost. The slide in general shows the very simplified storage I/O stack, which we don't have time to go through, unfortunately. For the purpose of this presentation, we'll only focus on the blocks on the DPDK side. Right. So SPDK, like the name suggests, it's a development kit. It's a set of libraries, each with different header, different, library. Yeah, and Well, even though it is shipped with a few applications which can handle the entire I/O stack from top to bottom, it is essentially a set of smaller building blocks. So let's start on the env in the bottom right. This is, well, env stands for an environment library. It's a set of different function wrappers for basic DPDK functionalities used everywhere throughout SPDK. That's, for instance, where SPDK malloc is defined. It's basically calling RT malloc inside. There's also a couple of function wrappers defined for DPDK mempools, DPDK rings, as well as a couple of function wrappers for PCI access. And the reason we have this extra abstraction is that some people wanted to integrate SPDK into their existing systems, existing environments, where DPDK simply could not be used for memory and PCI access, right? So we have this abstraction, and those people can swap it out. They can use their own implementation that doesn't depend on DPDK at all. We also have other libraries that depend on DPDK directly. We've got, well, precisely compression, encryption, and vhost, and those just include DPDK headers directly, but they are not essential to SPDK. If the user doesn't want to use DPDK, he can simply exclude those from building. He doesn't have to compile those. And then he doesn't have any DPDK dependency at all. Right, so all of those SPDK libraries, like I said, have a separate header, separate API, and they don't use any RTE structures, any DPDK RTE structures at all, or anything like that. In general, storage has slightly different use cases than networking, so SPDK defines its own various frameworks and design principles. Even though DPDK is used underneath, the SPDK APIs don't match underlying DPDK APIs one-to-one. There are some differences. In various cases, you could even say that SPDK tries really hard to integrate DPDK, and we'll get to see some examples later on. Yeah, and now I'll let Fiona talk about Cryptodev.
Okay. Hi, everybody. Yes, I'm going to talk about how Cryptodev is implemented, is used by SPDK. So if we just look at on the left-hand, the left-hand side here, and if you ignore the crypto part, first of all, I'm just going to have a quick explanation about what a block device is. So block devices it's a layer that abstracts away drivers and block devices underneath, and their specific APIs from the application. And up at the top, you've got this SPDK defined API. And you can think of an application as something that's going to send data down to a disk by telling the block device layer that it wants to store a certain amount of data at a certain logical block address. And the blocks on the disk are 512 bytes, or more recently, generally 4K blocks on the disk. And so the application is aware of that and will try and write certain things at a logical block address. So for the crypto device, it's quite simple. So you can build a layer above the block device. There's the capability in SPDK to do a virtual block device, which adds extra functionality onto what a block device does. And the crypto layer, you can think the application sends data down, it gets trapped by the crypto layer. This crypto layer has initially found what devices using the Cryptodev APIs. It's figured out which devices are available and has enabled them here. So it's just going to send the data across to the Cryptodev, called the Cryptodev APIs directly, and they'll be encrypted by either AS9 multi-buffer in software or the Quick Assist device in hardware. Comes back to the Cryptodev and it passes down to the device. So it's very simple. There's nothing terribly complex about it, and it just adds an encryption layer to the disk, and everything going to the disk gets encrypted. And generally, it can be in place. There's no reason to do out of place for encryption. So for just to summarize what happens then with encryption. It's cipher only. We don't have any chaining needed. There's no authentication. The algorithm that's used is AES-CBC. AES-XGS is a mode that's more commonly used by storage, and we've implemented it in DPDK so that it can be picked up by SPDK and it's on their backlog to be integrated. And yeah, the rest I've mentioned already. Okay, so I'm going to go on to Cryptodev. So for compression, it's an obvious use case for SPDK. You want to compress your data. It's much more complicated than Cryptodev, though, in the implementation. And the main reason for all the complication is that you don't know the size of your output. So with crypto, passing 1 kilobyte to be encrypted, it's going to come out as 1 kilobyte. There's no difference in size. For compression, you not only, it's going to be different size, you also don't know what that size is at the start. So this libreduce layer was added into SPDK to handle the mapping between where the application thinks that the data will be stored to where it's actually stored. So if we take an example of, say you're going to compress 15 kilobytes of data, and you pass it down. Now, if you didn't have your compression device, the application would believe 15 kilobytes is going to be stored on 4 sectors on the disk, so 4 logical blocks. And that's its expectation, and it passes down the logical block address of the first of those 4 blocks. So in this case, the compression traps that and uses libreduce to set up a mapping table between where the data, the application thinks the data is, and where exactly it's going to be on the disk. It doesn't know at this point how small that's going to compress down into, so it has to allocate buffers, destination buffer. It has to predict the size of the buffers and store them. And it stores them in persistent memory. And I'll come back to that persistent memory in a minute, why it's persistent memory. But it uses PMDK there to access the persistent memory. So yeah, so the application sends the data down. It's now going to send it over. It's going to send it over calling the Cryptodev API. Cryptodev compresses it, and let's say it compresses down to 3 kilobytes. That comes back, and the 3 kilobytes get written down onto the disk at a particular logical block address. And the data is stored then, by libreduce. So the compression would go back to libreduce and store that mapping between the application's view of where the data is stored to the real place the data is stored. So I said I'd come back to why persistent memory. If you can imagine that if this is a server and the server goes down and you've stored 3K, down in this disk somewhere, but you haven't kept track of where you put it except in volatile memory, then you're going to lose everything. So it has to be stored in persistent memory. Initially, in the first proof of concept, this was done onto a file on the disk, but that's not performant enough for a high-speed application. So there is persistent memory. There's a library. There's a whole. It's community again. Open source PMDK, which can be used to access persistent memory, and libreduce has built-in access to that. So that's been integrated in, and it improves the performance of where the data is stored. So another interesting use case for compression, it's the same use case, but if you imagine that 15K that we said was being passed down, if it got passed down and when it did the compression, it came back and it was 13K. It's still going to take 4 sectors on the disk. So there's no real advantage to storing it as compressed data. So it can be stored as uncompressed data. And again, the metadata to do that is kept track of in libreduce so that it knows when that data is requested afterwards, it knows not to decompress it, to just pass it straight back in as because it's uncompressed data on the disk. Okay, so said compression is a much more complicated implementation than crypto. I've mentioned about the output size. Yeah, the one advantage maybe over network compression, if you had network compression use cases, you may have blocks of data coming in different packets to be decompressed, and you won't know how much space you need to decompress it. And when you decompress data, it increases in size. So you have to handle error cases where you might not have allocated a big enough destination buffer. For compression, for this case, because you compress the data already, SPDK compresses it and then is later going to decompress it. It can keep track of how much data, how much space it's going to need to allocate for the output buffers on retrieving the data. So that is at least one simplification. Yeah, I think I've covered everything else in the slides, so I'm going to hand back to Darek to continue on.
Right. I think compression is a nice example of how DPDK integrates with a lot of foreign code base, SPDK code base, to deliver a single isolated service. All right, memory management. I've already mentioned SPDK malloc. Internally, it just calls RTE malloc and returns a memory that's memory buffer that's ready for DMA. Then we've got SPDK memory register function to make other memory DMAble, memory allocated through other means than SPDK malloc. And it calls RTE VFIO DMA map from DPDK, which makes the memory DMAble for local PCI devices. But it also calls some IB verbs APIs to make memory available to RDMA, and also shares the memory of connected vHost devices, so that the memory is DMAble in a separate process, a separate SPDK vHost process, for instance. Right, so we already start to see some differences between SPDK and DPDK. Yeah, and even if we consider just PCI DMA, well, SPDK memory register and RTE VFIO DMA map still have slightly different behaviors. For instance, RTE VFIO DMA map will immediately fail if it's called while there are no PCI devices attached by DPDK, which is a limitation of the underlying kernel VFIO interface, and it's understandable for DPDK to have such limitation as well. Well, but from DPDK perspective, when user calls SPDK memory register, he might only care about making memory available to RDMA. He may not care about PCI DMA at all, right? So we can't fail it if there are no PCI devices attached. But then, what if a PCI device is hot plugged and the user wants to do DMA to previously registered memory? For that reason, SPDK will keep track of all previously registered regions, and whenever a PCI hot plug happens, or the first in SPDK, it will call RTE VFIO DMA map with all those regions. Right. And even more differences are visible in PCI access. In SPDK, we've got those two functions to well, attach and detach a PCI device, and those just call the equivalent DPDK functions. But then what about hot plug? SPDK supports it, of course, and the usual UDEV hot plug and hot remove events are polled by the upper layers, practically by the NVMe PCI driver, not the env layer itself, not the low-level API. Yeah, and DPDK 1805 introduced an ability to poll the very same UDEV events, right? There was an event, device event monitor added, and it added this API function to register a function to be called whenever such UDEV hot plug and hot remove or hot remove event would happen. So at that time of DPDK 1805 release, SPDK was already having this UDEV code, and it couldn't just utilize the new, shiny, and cool DPDK API. The reason SPDK supports all still supported DPDK releases, even the ones without that function by then. So if the UDEV code had to stay in SPDK to support those older versions, DPDK versions, it could use the same code for all DPDK versions, right? However, at some point, DPDK started polling VFIO hot remove notifications, and those are just notifications for a different type of hot removal. And SPDK wanted to process those as well, because it didn't so far. However, the low-level VFIO interface to poll, to retrieve those events was abstracted away by DPDK, because it's DPDK that handles all the low-level PCI stuff. So here's what we've done. Oh yeah, one more thing. Those events, those notifications were only available with this callback register function. Right. So to support it, we internally in the env library registered this callback function, and we made it set a removed flag in a PCI device structure. And then it would be still the upper layer's responsibility to periodically check that flag and initiate the usual PCI shutdown and hot removal whenever it's set. So, well, the upper layer would poll UDEV events and check the removed flag to initiate hot removal. Right. Oh, one more thing. I guess SPDK will consider refactoring this PCI management after the last DPDK version without RTEDEV event callback register is finally deprecated. It finally reaches end of life, right? Then in SPDK we'll be able to drop the UDEV code directly and utilize the equivalent DPDK code all the way. Yeah. Well, one good thing about this design difference is that SPDK stresses PCI error handling path in DPDK a lot, and because of that, it was able to find a few issues in there that weren't necessarily visible yet within DPDK itself. Right. Then we've got vhost. DPDK's library for creating vhostnet devices. Most of its code implements a device-agnostic vhost user protocol, and SPDK wanted to use it for storage. We thought a few additional APIs in RT-vhost would suffice for all the SPDK use cases, and DPDK initially agreed to add those APIs, but then the more we tested, the more issues we found. Yeah. For a long time, SPDK was shipped with an internal fork of RT-vhost that had a few storage-specific workarounds applied on top. And DPDK didn't want to include those workarounds in upstream because while those changes were enabling the storage use case, they were also slowing down networking use case. They were slowing down vhostnet, so it's understandable. Yeah. Eventually, here's what we've done. In DPDK 1905, we added this function that is capable of hooking directly into the RT-vhost code, and SPDK with it is able to say that those messages should be handled differently, and we are still able to apply the same workarounds, storage-specific workarounds. It's just that there are no code changes inside RT-vhost required, and vhostnet doesn't have to suffer. There's no wrap-up. Any questions?
Hello?
Hello?
Do you have plan to introduce your erasure coding management with SPDK?
Sorry, say again?
The erasure coding.
I didn't catch that.
Erasure coding.
English.
The erasure encoding, do we have plans to put it into CompressDev or into SPDK? I think actually I'm not sure if SPDK has it. I know the ISL library has erasure encoding, but SPDK, I'm not sure if it uses it or not. You don't know? No?
No, I don't.
I guess it's outside our area of expertise, but we can ask the people if you talk to us afterwards and get you the information. It's not planned in DPDK anyway, under CompressDev. We did look at it briefly. It's in SPDK. Yeah. I know it's in the ISL library, but sure. Actually, I have a question for the audience, for anyone who's interested. So I posted a proposal to remove the experimental label from the Cryptodev API a while back, and there's been an overwhelming response so far. So if anyone has an opinion on it, let me know. I'm in two minds. I'm not sure. There's pros and cons, and obviously a lot of this discussion about API breakages is making us nervous about removing experimental labels before it's necessary. So yeah, I'd appreciate any feedback from anybody on that. Okay, I have one more comment on wrap-up then if there's no more questions, and that's that in Cryptodev, one of the things we did work on in the last year that we didn't really have time for in this presentation was a compression performance tool. So if anybody wants to try out compression and run the performance tool, that's available, similar to the crypto performance tool, and takes input files, and you can use the standard Calgary corpus or Canterbury corpus or whatever files you want and compress them and see what the performance is. So.
Yeah, actually, since we've got time, I can tell the amount of work to properly fix vhost was huge. It would be a huge undertaking to fix it properly. At one point, I proposed a new library, RT-vhost2, well, with 2 at the end, that would suffice for both networking and storage. It would provide a much lower level API, but the library was eventually rejected. Yeah, so that's why we ended up adding this hacky API. I don't think anyone is happy with it. It's very hacky, well, but it works.
Okay, thanks everybody.
Thank you.
Oh.